So, some laws and rules for exponents involving integral, that is integers exponents. And we remember our rule, if we have b to the x times b to the y, we add exponents, that's b to the x plus y. Example, 2 to the 5th times 2 to the 17th equals 2 to the 22nd. B to the x over b to the y is going to be b to the x minus y. Subtract the exponents. For example, b to the 10th over b cubed equals b to the 10 minus 3, or 7. If we have b unequal to 0, 1, or negative 1, b to the x will equal b to the y if and only if x equals y. That means, or if and only if means, if b to the x equals b to the y, then x equals y, provided that b isn't 0, 1, or negative 1. And if x equals y, then b to the x will equal b to the y, provided that b does not equal 0, 1, or negative 1. Some other rules: if I've got a product being raised to a power, that's the product of raising each of the two factors to that power. For example, 2 times 4 to the 7th will equal 2 to the 7th times 4 to the 7th. And also, if we have a fraction raised to an exponent, that will be the numerator raised to that power over the denominator raised to that power. So, for example, 3/7 raised to the second is going to equal 3 squared over 7 squared. And for a is unequal to 0, a is greater than 0, b is greater than 0. If those are true, we're told that a to the x equals b to the x if and only if a equals b. In other words, look at my if and only if again. There's two if-thens. If a to the x equals b to the x, then certainly would make sense that a will equal b if your exponents are equal, and then your bases are going to have to be equal. And conversely, if I've got two numbers that are equal, if I raise two equal numbers to the same base, I should get, or to the same exponent, I should get the same result. So our last rule is, suppose you have some exponential expression raised to a power. What you're then going to do is simply multiply your exponents, x times y, and that will give you your result. So I'm looking at, for example, 2 cubed raised to the 5th power. That would be 2 to the 3 times 5, or 2 to the 15th. That should make sense, because if you look at 2 cubed to the 5th, that's going to be 2 cubed times 2 cubed times 2 cubed times 2 cubed times 2 cubed. And then if I use my previous rule, where I add exponents, that would be 2 to the 3 plus 3 plus 3 plus 3 plus 3, which would be equal 2 to the 3 times 5, because there are 5 3's, which equals 2 to the 15th. So suppose I got $100, and I'm told it's going to increase at a 77.2% rate per year. The question is, how much am I going to have after 12 years? I think we want to realize that if we multiply something by 1.072, that means that in essence I'm increasing that something by 7.2%. If I multiply something by 1.39, I'm going to be increasing it by 39%. So in this case, I then am looking at the $100. At the end of the first year, I multiply 1.072, and I'll get whatever I get. I would then take that money that I just got, this 100 times 1.072, I'd multiply that by 1.072 again to get what I'd have at the end of the second year. So in the end, how much am I going to have after 12 years? I'm going to have the 100 times 1.072 raised to the 12th, which turns out to be whatever that is. So we have something decreasing at a constant percentage rate per year. Let's suppose I have a $7,000 motorcycle I've just bought, and I know I've been told it's going to decrease at 4% per year. I want to know how much my motorcycle is going to be worth after 10 years. Well, if I decrease at a 4% rate per year, that means I'm actually going to maintain 96% of my value. If I maintain 96% of my value, I would multiply by 0.96 to indicate a 4% decrease. After the first year, once I have that amount of money, 96% of what I started with, I'd multiply that again by 0.96 to get how much the motorcycle would be worth after the second year. So, to get my answer here for what's going to be worth after 10 years, I've got my 7,000, and I'm going to multiply by 0.96 raised to the 10th, and that turns out to be whatever it turns out to be. And again, if you want to, say, have something decrease by a rate at 10% per year, you'd have 90% of it left, you'd multiply by 0.9. Something decreases at 30% per year, you'd have 70% of that left, you'd multiply by 0.7 to represent that 30% decrease. So you might remember that any base raised to a power of 0 equals 1. And we might just want to consider why that happens to be. If I have 2 to the x over 2 to the x, clearly something over itself, or 3 to the x over 3 to the x, or a to the x over a to the x, clearly that equals 1. Well, if I use my rules of exponents that we've just learned, 2 to the x over 2 to the x is going to be 2 to the x minus x, or 2 to the 0. So I need to somehow define and make this consistent with the fact that 2 to the x over 2 to the x equals 1. Well, therefore 2 to the 0 equals 1. So we know that a base raised to an exponent negative 1 is simply going to reciprocate that expression. So for example, 2 to the negative 1 is going to be 1/2. Well, I mean, let's just think a little bit about why that's reasonable with some of our exponent laws that we've just seen. 2 to the negative 1 I could write as 2 to the 0 minus 1. I could then use my rule that 2 to the 0 minus 1 is 2 to the 0 over 2 to the first. And 2 to the 0 is 1, and 2 to the first is 2. So therefore 2 to the negative 1 equals 1/2. I could do the same here with 3 to the negative 1 getting to 1/3. And I could generalize it, a to the negative 1 getting to 1 over a. So in other words, an exponent of negative 1 reciprocates my base, so I get 1 over a. So problems 46 through 49, there's going to be a few factoring problems involving some exponential expressions, and they're looking for you to see a quadratic pattern. An example of that, suppose I give you 3 to the 2x minus 3 to the x minus 6 equals 0. I've got to see this 3 to the 2x is 3 to the x quantity squared, and then a 3 to the x. And you'll notice I have something squared minus something minus 6. If I let w equal 3 to the x, pure substitution, I'm going to get a quadratic here. W squared minus w minus 6 equals 0. So I'm going to do just a pure substitution, and I'm seeing that quadratic pattern. Go ahead and work your quadratic down, and then substitute your 3 to the x back in for w, and you get 3 to the x equals 3, which means x equals 1. 3 to the x equals negative 2. 3 raised to any power whatsoever can never yield a negative number, so there's no answer. That's an extraneous solution. Not going to work. So I get a sole answer of x equals 1, and I can put that back into my original equation up here and check it. 3 squared is 9, 9 minus 3 is 6, and 6 minus 6 is 0. It checks. And once again, in those 46 to 49 problems, to get that quadratic pattern, at times they're really going to hide it by giving you your exponential expression in the denominator of a fraction. It's got 2 over x and reciprocal 2 over x. Key here is just to multiply. Go ahead and multiply through and clear that 2 to the x out of the denominator, which makes sense. You might want to clear fractions anyway to clear denominators here. So if I multiply everything through by 2 to the x, 2 to the x times 2 to the x is 2 to the x plus x, or 2 to the 2x. 2x times 1 over 2x is going to give you just 1. And 2 to the x times 7 is going to give you 7 times 2 to the x. Go ahead and rearrange those terms now. 2 to the 2x minus 7 times 2x minus 1 equals 0. Note that's going to be 2 to the x quantity squared minus 7 times 2 to the x minus 1. If I go ahead at y equal 2 to the x, I've got my quadratic pattern, y squared minus 7y minus 1 equals 0, and I could go ahead and try and solve.